A series is a sequence of partial sums. I'm sorry about all the S's. It's a sequence of partial sums. Partial sums of what? Of a sequence. The sequence of partial sums of a sequence. Sorry about that, but that's what it is. So I've got this sequence written here on slide 15. I called it A sub n. It goes 1/2, 1/4, 1/8, 1/16. I think you know what's going on there. I'll write down what my terms are. My first term, which I would notate that A sub 1 is 1/2. My second is 1/4. My third term is 1/8. My fourth term is 1/16. What would my 10th term be? When I look at what's going on here, the third term is 8, and the second term is 4, and the first term is 2. And those can be rewritten as 2 to the 1, 2 to the 2, and 2 to the 3. In the numerator, I've just got 1, so A sub 10 is probably 1 over 2 to the 10th, whatever tiny little number that is. A sub n then is 1 over 2 to the n. Now I know that this sequence converges to 0. And I partially know that because the sequence is geometric. Why is the sequence geometric? Because it has a common ratio. The word common is very important. That means each time here, I am multiplying by the same number to get the next number. It is always 1/2 all the way through. That is my common ratio. In this case, my common ratio is 1/2. Because the absolute value of 1/2 is less than 1, the sequence necessarily converges to 0 because it's a geometric sequence with a common ratio less than 1 in absolute value. So the sequence converges to 0, but that's not the question. The question is for me to try to find this. Now to break that down, what that's saying is add up. Sigma means add up all of the terms where you take the first term first, A sub 1, and then add that to the next term. This symbol, sigma, means that your inputs are 1, 2, 3, 4, 5, starting with whatever this is, in this case 1. The next one would be add A sub 2, add A sub 3, plus continue, and then this notation tells me that I'm going to stop on the nth term. So the last term I'm going to have is A sub capital N. N is not telling me what the term is, it's just telling me what number term to start on. 1, 2, 3, what to stop on. The number term N, okay? So that's a partial sum is what that is. That's a partial sum. Why is it a partial sum? Because N is some number. It's not infinite. Okay, so we're not looking at the infinite series, we're looking at a part of that series. Just stop it at some point at n. So in order to figure out what that formula would be, I need to write a formula for the partial sum. And if I'm going to write a formula for the partial sum, I have to calculate them just like I did with sequences. The first sum is take the first term and add it to nothing. So the first sum is just 1/2. The second partial sum is take 1/2 plus 1/4, the sum of the first two terms, A sub 1 plus A sub 2. The third partial sum is take A sub 1 plus A sub 2 plus A sub 3 also. Now I have added those and found common denominators, and this is what I've got. So S sub 1 is 1/2, S sub 2 is 3/4, S sub 3 is 7/8, S sub 4 would be 1/2 plus 1/4 plus 1/8 plus 1/16, and that gives me 15/16 when I add it. A sub 1 plus A sub 2 plus A sub 3 plus A sub 4. This is forming a sequence of itself. 1/2, 3/4, 7/8, 15/16. Now I want to try to write the nth term in that sequence. So I'm going to try to look at what's going on with these numbers. The top is 1, 3, 7, 15. It's not odd numbers, right? Because it skipped over some odd numbers. It's not that. But I can see that if I were to add 1 to the numerators, I would have a power of 2. So I'm going to call the numerator formula 2 to the n minus 1. Let's see if I'm right about that. 2 to the 1 minus 1 is 1. 2 to the 2 minus 1 is 3. 2 to the 3 minus 1 is 7. 2 to the 4 minus 1 is 15, right? And in the bottom, I've just got 2 to the n. 2 to the 1, 2 to the 2, 2 to the 3, 2 to the 4. So that formula will work for my nth partial sum. So the question is, what would happen if I didn't think of this as a partial sum, but as the entire sum? This is the formula right now for the nth partial sum. If I plug in n equal 4, it will give me 15/16, the sum of the first 4 terms, for example. So now I'm trying to figure out, what would that be? What would the sum of infinitely many terms be? So if I want the sum of infinitely many terms, I can't add infinitely many, but I can take the limit as n approaches infinity of the nth partial sum. And my nth partial sum, I have a formula for. And I want you to look at that limit and think about it. I can already see from these numbers that they're always like a fraction that's near 1. Are they getting nearer 1? 15/16 is only a 16th away from 1. 7/8 is 1/8 away from 1. 3/4 is 1/4 away from 1. So because this is only 1/16 away from 1, I think that this limit is approaching 1. Now I can check out what's going on by using that desmos sketch, and I can see if that actually is the case. If that's the case, then we can say that the sequence converges to 0, and the series, and that's the infinite series. When I say series, I mean infinite series, converges to 1. So if I added up infinitely many of the terms of this sequence, it's going to approach 1. Let's check it out on Desmos. So I'm going to go to my slide 15 here and find my Desmos sketch link and open up that Desmos sketch. You should bookmark this sketch. It's a pretty important sketch. We're going to use it a lot. I put my sequence formula in here. Remember, it was 1 over 2 to the n was my sequence formula. Except for instead of putting n, put x, okay? And what this sketch gives us is in orange, it gives us the sequence, which we can see is approaching 0. I can see that those values are approaching 0 in the graph. I can also see it in the table. I can show even up here in 500, 1,000, and 10,000, those are numbers very, very close to 0 in scientific notation. In the second column in black, it has the thing that we're most interested in, which is the series. And first, I'm just looking at the first partial sum. That's just a half. The second partial sum, a half plus a fourth is 3/4. The third partial sum, a half plus a fourth plus an eighth is 0.875. And sure enough, those sums, those partial sums, seem to be moving towards 1, both graphically and in the table. So I have verification of what I've learned to be true, which is the sequence is converging to 0, but the series is converging to 1.